Amanda, can you hear us?
Yes, I sure can.
Good. Did you see Cynthia asking in the chat if other people can use the same link to view the presentation?
Yes, I sure can. Oh,
Awesome. So is that going to be okay? Did you see Cynthia asking in the chat if other people can use the same link to view the presentation?
sorry, we're getting a whole bunch of echo. I'm going to communicate over chat, okay?
Awesome. So is the feedback is so bad.
Liftoff of the Delta rocket carrying Blast. 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 Liftoff of the Delta rocket carrying Blast.
Hello, everyone. Sorry about the weird technical issues. My name is Amanda Schlindwein. I'm the executive assistant at Big Brothers Big Sisters. And hello, teachers and students. Welcome to Big Brothers Big Sisters of Central New Mexico Discovery Festival 2021. Quick shout out to Nexus Brewery for letting us use a spare room in their amazing restaurant. Great food and drink here, so stop on by to support local business. This morning, we have Jennifer Tyrell and the Defense Threat Reduction Agency here to give us a shocking demonstration of a Van de Graaff generator. Jennifer, go ahead and take it away.
Thanks, Amanda. We appreciate that. I've got somebody here with me to help me out today. Hi, I'm Manon. And I'm Jennifer, as she said, and we are here with the Defense Threat Reduction Agency, or DTRA. DTRA is a part of the Department of Defense, and they play a very important role in keeping all of us safe and in our national security. And it takes a lot of really smart people with backgrounds in science, technology, engineering, and math to make those things happen. So DTRA has a vested interest in making sure that you all, the future STEM professionals of America, have a good background in STEM. And that's why we're here today to teach you a little something cool. So we want to start this off with a little experiment, I think.
Yeah, Jennifer, it looks like you brought something pretty cool here this morning.
I do have something cool. This machine that you see on our table here is a Van de Graaff generator.
A Van de Graaff generator? You know, now that you say that, I think I have heard of the Van de Graaff generator. This produces and creates static electricity.
Yeah, that's exactly what it does. I think we should see it in action a little bit. Nick, do you think you can hit the light for us? We hope that you all at home were able to see those sparks flying.
Wow, that is so cool. You know, it would be interesting or great if we had time to talk a little more about this Van de Graaff generator, make a few observations, and maybe even conduct an experiment.
I think that that is a great idea, and we definitely have time for all of those things today. You mentioned that you thought that this was producing static electricity, and it is, just like whenever you scoot your feet across the carpet and then you touch a doorknob and you feel a little spark.
Yeah, I think I've done that with a balloon too.
Absolutely.
Okay, well, I guess before we get started with discussing this, because this looks really, really involved, it's probably a good idea to start at the beginning with matter. And matter is anything that has mass and takes up space. And when I think about matter, I have to remember that matter is made up of atoms. And an atom has three components: protons, neutrons, and electrons. Protons have a positive charge, neutrons have a neutral or no charge, and electrons, they have a negative charge.
That's exactly right. And I think that it would be helpful before we move on any further with this demonstration for you to join us in creating an atom model so that you can better understand it. So if you have a piece of paper and something to write with, grab it. That's all you need for this. It's a pretty simple model. So take your piece of paper, and what we're going to do is tear off a little chunk of paper, about like this. And we're going to take that chunk of paper and we're going to tear it into 6 parts that are just roughly equal. And we'll put those on our table. All right. These 6 pieces of paper are going to represent our protons and our neutrons. So as Manon said, protons have a positive charge. So I'm going to write a little plus on here. Protons with a positive charge. And I'm going to go ahead and do that for 3 of these pieces of paper to represent the protons that are in this atom. Along with the protons, we also have neutrons, and we can represent the neutrons with an N. Remember that neutrons are neutral. They don't have a charge. So I'm not going to write a plus by them. The protons and the neutrons in an atom are arranged in the nucleus and are pretty tightly packed. So take your protons and neutrons and put them all together, crammed together in the nucleus, where it's very hard for them to separate. But we have three parts of an atom. So in addition to the protons and neutrons, we have electrons. So we'll come back to our piece of paper, and this time we're going to make some much smaller subatomic particles to represent the electrons. So I'm going to get three little bitty pieces of paper, much smaller than the protons and the neutrons, and put them on the table. And I'll label those with an E for electrons. And do you remember what charge electrons have? If you remember, you can tell us in the chat. We would love to hear from you. The electrons have a negative charge. And the electrons in the atom are not in the nucleus with the protons and neutrons. They're far outside the nucleus, and they spin around the nucleus constantly, very quickly, out here in an area that we call the electron cloud. And so as you can see, this atom is mostly empty space. And these electrons, as they're moving about in the electron cloud, are readily able to leave the atom and move to a different atom. They can jump from atom to atom or flow between materials. In this current atom that I have three positive charges and three negative charges. They cancel each other out so that this atom is neutral. But what if I lose an electron? Now I have more positive than I have negative. So this atom is positively charged. If I gained another electron from the person next to me, you could grab one from somebody if you want, then I have created an atom that now has a negative charge, more negatives than positives in our subatomic particles. This is a great way for us to think about atoms so that we can understand what's going on in the Van de Graaff generator. Thanks for helping me in making an atom model. Let's see if we can relate this now back to our Van de Graaff generator.
Okay, so we know that matter is made up of atoms. And this Van de Graaff has something to do with atoms. We know that. And well, I have my Barbie here, and Barbie is matter.
That's right. Barbie's matter, and she's made.
And if this has something to do with atoms, what if we take Barbie on an adventure and introduce Barbie?
That sounds like a plan.
What do you think will happen?
What do you guys think? Let us know in the chat. Put Barbie on Van de Graaff generator. What happened for atoms? Because she is matter and made of atoms.
Well, we saw a shock at the beginning. We'll see sparks.
That's a good thought. Let's give it a try and see.
Whoa! Okay, well, definitely no sparks. But did you check out her hair? Her hair was going crazy.
What in the world was happening with her hair?
I don't know. It's down now, but it was like clearing out when she was on top of the Van de Graaff generator. It'd be so cool to be Barbie right now.
I want to do it, but I'm way too big to sit on top of this Van de Graaff generator. What do you think would happen if I just touched it?
Well, let's see. Go ahead, touch it.
Okay, I'm going to turn it back on. It gave me a shock.
I heard it. And like a little bit of your hair is starting to stand up too.
Oh no, my hair! What's going on with this? Let's turn it off. What in the world could be making Barbie's hair stand up and make this shock me and make my hair start to stand up?
You know, if we think back to what are atoms,
Yes.
and we talked about how protons have a positive charge and electrons have a negative charge, then maybe something is happening with the charges. I know that if we have atoms, or if we have charges that have opposite or different charges, that they attract.
I have heard that opposites
Okay.
attract.
And so, me too. But if they have the same charge, then they repel each other. Let's look at these set of magnets that we have. Okay, so if we allow this to demonstrate what's probably happening with our atoms, we can see that we have two ends. We have an end that's red on each one, and then we have a silver end. If we say that the red is positive, then when we bring them together, we will notice that the other magnet is scooting away or trying to get away from it. They're repelling each other. But if I take the opposite end, if I have a positive and a negative, and I start to bring it close, then I see that it actually attracts. And if I go slow enough, you can see that without even moving, if I come and I stop, that it draws the opposite to itself.
That's really awesome. And I think that the magnet is a great way for us to illustrate what's happening in the Van de Graaff generator. As we talked about, the Van de Graaff generator has positive and negative particles because it is matter and it's made up of atoms. The Van de Graaff has this belt inside of it. And as the belt is spinning around and around, it's creating an awful lot of friction, just like scooting your feet on carpet whenever you shock yourself on a doorknob or a light switch. So what happens is that we end up with a positive charge on the dome because we've lost electrons to the moving belt. When we lose electrons, we build up a positive charge. And then whenever I touch it, this just really wants to be neutral. So the electrons move from me to the dome and cause me to have a positive charge, or the Barbie to have a positive charge.
Okay, I understand. I got it. So I saw what happened with Barbie, and I heard the shock when you touched it, probably kind of electric, and your hair did start to move a little bit. And so you and Barbie both have hair. I wonder what would happen to an object that didn't have hair.
Well, luckily for us, they're a great way to figure out an answer to a question. And we use something called the scientific method. I'm sure you've heard of the scientific method before, right? Let's see. It looks like we might have a question from someone before we move on to the scientific method. Amanda, is that a question that you're going to share with us verbally?
Yes, thank you, Jennifer. So the first question, actually, you kind of answered already. Jess from Albuquerque was asking, so how you can create this sort of reaction at home. So you mentioned sliding your feet with socks along the floor. Is there any other way to create this same sort of principle in your own home?
Yeah, great question, Jess. I'm so glad that you asked that. Shuffling your feet is an easy one to think about, but another one that we like to talk about is taking a balloon and blowing it up and then rubbing it on your shirt. And then if you bring that balloon that's been rubbed on your shirt close to your hair, you can get your hair to stand up. You can also use that same thing to bend water out of your faucet. There's a lot of fun that you can have with static electricity, and I'm so glad that you asked that. We're going to have a little bit more fun with electricity here. Keep your questions coming. I love that one. So we are going to switch gears and start talking about the scientific method.
Yes.
Which is going to be a way that we can answer a question that Manon posed about what might happen with something that doesn't have hair. There are 6 steps in the scientific method. The first step is to make an observation and ask a question, which we've already done. The second step is to do a little bit of research And that research can come in the form of some of the stuff that we've already done today and talked to you about. Then we're going to form a hypothesis, which is a time that we predict what we think is going to happen. Then we'll test our hypothesis. And that is my all-time favorite part of the scientific method, because we get to do the experiment and see what happens. After the experiment, we analyze the data and draw a conclusion so that we can report our results and communicate it with other people. So I think that we can go through the scientific method here and answer Manon's question about what would happen to something that doesn't have hair.
Okay, so if we get started, if I start to walk through it, then I've made some observations.
Yes.
I saw Barbie and I saw you, saw what happened with the hair, and I heard the shocks. Okay. Well, part of the observations and the research can be what we saw happen with the magnets and with your atom model, with the protons and the neutrons and the electrons. And so I use all of that to ask the question, so what would happen to an object that didn't have hair? Do we have an object? Because it'd be great if we could be more specific with our question.
Yeah, I think that our question is not very specific. I do think that we filmed about baking.
Okay.
So why don't we try pythons? Do pythons have hair?
Nope. Okay, so our question is, what will happen when we place pythons on the Van der Graaff generator?
I don't think we can place the pythons directly on the Van der Graaff generator because it is a dome.
Yeah.
And as a dome, I think that they'll just fall right off.
Yeah, I think so too.
So luckily we have this handy stand, which gives us a nice flat surface that we can set the pythons on.
Okay.
Yeah, let's put it on there. Now we have to form a hypothesis.
Right. Okay. So now I'm going to draw from all of my observations, my experiences, and the research for what I know. And well, these pythons don't have hair, so I don't think that the hair is going to stand up or go crazy. But maybe the pythons will just stand up. Yeah, I think the pythons will stand up.
All right, I think that's an okay hypothesis. Let's ask you all, is there something that you can tell us? What is your hypothesis for what's going to happen here with our pythons? Take a minute and put something in the chat so that we know what your hypothesis is.
This is going to be really cool.
Hey, Nick, can you bring us back so that we are showing this? We're going to save that PowerPoint for a little bit later. All right, hopefully you have a hypothesis for what you think is going to happen here to our pythons. Are you ready?
I'm ready.
Whoa!
Oh my goodness, those were like flying saucers everywhere. So it was a little bit different than what happened with Barbie. And my hypothesis wasn't exactly correct.
Well, that's okay. Your hypothesis doesn't have to be correct. We've still learned something really neat. What do you guys think was happening with these pythons? We know that, like Barbie, the pythons are matter, and so they are made of atoms. And so when the Van der Graaff generator turned on and became positively charged, the positive charge is looking for electrons somewhere and snaps them from the pythons. So what do the pythons become?
Positively charged.
That's right. And if we think about what we saw with the magnets, like and like are going to
repel each other.
And then we get this really cool flying saucer
flying saucers. Okay, can we see that one more time?
Yeah. Do you guys want to see it again? Okay, here we go.
Even cooler than the first time. That was great. I'm gonna just pick these up so I don't step on it.
Yeah, I think that was a really neat thing for us to do. We were using metal pythons. So now we've seen Barbie and we've seen metal pythons.
Okay, so like Barbie's kind of plastic and had some cotton for her clothing. And you touched it and you're a different material. And then we had the pythons Well, I wonder if we used a different material.
All right, what do you have in
Okay.
mind? Let's try something else.
Okay, what about if we use these streamers?
Perfect. Paper streamers. I
Yes.
love it.
Okay, and so what if we place the streamers on top of the Van de Graaff?
I think that we might have a similar problem that I was worried
Yeah.
about with the pie tins, where it just falls right off.
Yeah, okay, that's probably not gonna work. So how could we get it to stay on top to watch what happens?
I do have some magnets, and the dome of the Van de Graaff generator is metal. So the magnet sticks to the metal, no problem. So I think that this magnet will hold our paper down. And what do you guys think is gonna happen whenever we turn on the Van de Graaff generator? Should we see? Let's do it.
Look, it's my octopus. Let's see if the octopus likes me. The octopus is following my hand.
Oh my goodness.
I like my octopus.
I think the octopus likes you back. Well, this is really cool doing all these experiments and observing what's happening, but I'd like to explain it a little bit more. I think that this all has something to do with electricity. And I'm thinking about electricity, which we all come in contact with every single day. We use it for our lights. We use it to run various appliances. And right now, it's even making the Van de Graaff generator work.
Yeah, it is. It's running really well because of electricity. Well, when I think about electricity, I think about Benjamin Franklin. And I think about how he discovered the relationship between lightning and electricity. And I remember learning about his famous kite experiment. In 1752, he was out in a thunderstorm. He had a kite with a string and a key at the end. On top of the kite, there was a metal rod or metal wire at the top that was about 1 foot long at the top of the kite. And so he flew the kite in the storm and the kite was up in the clouds. Well, as the kite was up in the clouds, it drew the electricity from the clouds and it passed down and through the kite to Benjamin Franklin. And he got a shock, kind of like shock that you got.
A shock from the clouds. Well, I think that metal rod is really important in that story.
It is?
Yeah, that metal rod is a material that's called a conductor.
What's a conductor?
A conductor is a material that lets electric current flow through it. And that occurs because of the makeup of the atoms.
Okay, so if it's because of the makeup of the atoms in the conductor in that metal, well, what are the characteristics for those atoms?
That's a really good question. Metal is often held together by something called metallic bonds. And metallic bonds have different properties than other types of bonds, like ionic and covalent bonds. In a metallic bond, the electrons are free to move from ion to ion. So when electrons move, we're also carrying the electricity.
Okay, so I'm thinking back to your atom model, and I saw how the electrons were moving around freely. So it makes sense if they're moving freely that they're carrying the electric current with it. But I heard a term I'm not familiar with. Ion. What is an ion?
That's a really excellent question too. An ion is an atom that has gained or lost electrons. And as it gains or loses electrons, it changes its charge. This happens because of something called the Octet Rule.
Octet, like my octopus?
That's right. The prefix oct does mean 8, but in this case, it's 8 electrons and not 8 octopus arms.
Makes sense.
Based on the Octet Rule, atoms are always trying to make sure that they have 8 electrons in their outermost shell, which is called the valence shell of the atom. And so the atom will gain or lose electrons to try to reach that stable position of having 8 electrons in the valence shell.
Okay, so electrons move freely, and each atom wants to try to have 8 in its outermost shell. And if the atom doesn't have 8, then it will gain or lose electrons to make 8. And let me guess, I'm pretty sure that the atoms will take the easiest route to make 8.
Absolutely. Everybody wants to take the easiest route. We've got 2 more questions right now from people. Do you think this is a good time to pause? Yeah. Let's see what we've got, Amanda.
Yes, hi. So we have a couple questions. The first one is from Tyler in Farmington. He was asking, is the weight of the objects a factor in these reactions? So like you put the pie tins on and the streamers on and they're fairly lightweight. Would the reaction be different if they were heavier?
Okay, so that question cut off a little bit, but I think we got the gist. Absolutely, weight is a factor in this. If we put something pretty heavy on this, there wouldn't be enough charge building up to make it flow away. That's a really excellent question. And that's kind of illustrated with our magnet here holding this down, right? It's not weight holding it down, but the force of the magnet that's holding it down. But it doesn't build up enough charge to make the whole thing fly away. Really good question from Farmington. I appreciate that. Did you have another one for us, Amanda?
Yeah. We have one from Margaret here in Albuquerque. She was asking what creates the sound of static electricity, like that crack sound?
Oh, good question. We're going to get to that one in just a minute. Can we hold that question, Margaret? We're going to get to it. And if you don't like our explanation, let us know. We'll give you a little bit more.
Yeah, absolutely. And actually, Sarah Resnick is a teacher at Taylor Middle School, and her students are asking how you guys use static electricity at DTRA.
Oh, that's a great question. Can I ask us to hold that one for a minute too? We're gonna get to those a little bit later. I'm going to jump back into this where we were talking about our conductors and our insulators, and we're going to see if we can answer both of those questions a little bit later. Good ones, guys. Okay, keep them coming. So we were just talking about how all of the electrons are going to take the easiest route to get from not having 8 to having 8 electrons in their valence shell. All right. So let's see, if we definitely know that they're going to take the easiest route, then what would be the easiest route?
Well, if it's sitting on top of there and it became positive, right? And when I placed my arms around it, then I was getting close to it.
And electrons are moving, but they are more likely to move through something that is a good conductor.
Yeah, okay. And if it's moving through a conductor, then they are moving freely and they would transfer the current.
That's exactly right. As the electrons are moving electrons are electricity. So electrons that can move through metal more easily than they can move through some other materials like plastics.
Okay, and let me guess. So if it can't move through plastics, then plastics are insulators. Okay, and so maybe the characteristics of the insulators is that the electrons are not moving as freely. And so they're not letting the current pass through it.
That's exactly right. Conductors are saying, go. They're like a green light to electricity, and the electrons move so freely through it that the electricity just goes. But in an insulator, they're like a red light saying, stop. The electrons here are not moving, so the electrical current does not pass through. We've got a great example here of conductor and an insulator in this grounding rod that we are using for our Van de Graaff generator.
Grounding, like ground that we're standing on?
Exactly like the ground that we're standing on. This grounding rod is connected to the Van de Graaff generator at the bottom, at the ground, so that there is a path for electrons to flow. A very easy path for electrons to get from the ground to our grounding rod and jump over here to the dome of our Van de Graaff generator. So let's look at that again, what we looked at earlier, and try another experiment. You saw us make sparks earlier. It was so cool.
Yeah, it was really cool.
So
It's still cool.
what happens if we use the other side? You guys see a spark?
No, that side's not as exciting.
So why do you think we might want to have an insulator on the handle of our grounding rod?
Well, probably to keep you from getting shocked over and over again.
That's exactly right. It's going to stop that flow of electricity and keep me from being shocked. So we do see that we've got this shock that's happening from the dome to the metal part of the grounding rod.
Okay, this is all coming together. It's making sense. So now that I think about lightning and how lightning is electricity, and when I think about a storm with lightning and electricity, I also think about thunder, that big boom sound that we hear. Well, we kind of hear a shock, hear a little one, but if we have a large transfer, if we have all the electrons shooting through the air barrier, it's making that big boom that we call thunder. Thunder, lightning. Well, and then it makes sense now that we see the lightning before we hear the thunder, because light travels faster than sound.
That's right.
Wow. And then if I think back to what I've learned with my octopus here, I love my octopus, that the octopus was becoming positively charged because it was touching and sitting on top of the positively charged dome.
Mm-hmm.
So then all of the arms on my octopus became positively charged, and like the magnet, the like charges repelled each other and they wanted to separate. But then here I came and I'm standing on the ground, so I was kind of like the grounding rod, and it was reacting to me.
That's exactly right. Not only was it just reacting to you, it was stealing electrons from you in order to become neutral because it did not like being positive.
Wow, this is amazing. I'm learning so much. Well, we didn't try it with the grounding rod, right? So let's see. If I think that it would react, it's reacting to me like it would react to the grounding rod, I guess we should actually try and introduce my octopus to the grounding rod.
All right, let's give it a try. Here's our octopus and the grounding rod.
Yep, it's kind of attacking it. Oh yeah, it's all of the arms are getting on the grounding rod. I wonder if it likes the grounding rod more than it likes me. Well, it's still my octopus.
I don't think the grounding rod is going to argue with you on that one. But what's happening here is that the electrons are moving from the grounding rod to the octopus, or from the grounding rod to the dome. And so you all asked about the sound that you were hearing. That sound is electrons moving through the air, creating a sound wave, just like what happens whenever we have thunder. So that sound that you're hearing is moving electrons. Man, this is really cool.
I know. I'm learning a lot. And if I continue to make observations now, because I want to stay thinking scientifically, I want to stay with my scientific method.
Mm-hmm.
And as I make observations, it's natural to have another question.
I think that's exactly right. I think we can go back to our scientific method and we can make some observations and ask a question, but then we need to be able to do some research.
Okay.
So let's see if we can first ask a question that will help us learn a little bit more about electricity.
Okay. I'm going to use my observations. I'm going to make a really good question. Okay. Walk through this with me, students. Okay. We've seen Barbie and we've seen you, Jennifer, touch the Van der Graaff. We've had my wonderful octopus that I'm taking home with me. And we've seen how it has reacted. We've learned about protons and electrons and their charges and how like repels, but opposites attract. And we've seen different materials like the tin for the pie tins.
Mm-hmm.
Barbie was a different material. You're a different material. And then we had my paper octopus.
Mm-hmm.
Well, I wonder if we chose another material, because it's always fun to do an activity or something that maybe we can explore the same concept, but in a different way. So let me think. I want to choose something that they could do too. So let me think of a material. How about something that we use every day? It helps us when we shower. We should be consuming a lot of it each and every day.
I think I know what it is.
Do you know what I'm talking about? Yep, good old H2O. I think we should use water as part of our next experiment.
Okay, I think it sounds good to use water, but I would like to be safety minded, and I would not like to use water with my Van de Graaff generator.
Okay, but is there still a way to test and see if water will conduct electricity, if it's a conductor for electricity?
Absolutely. I am confident that we can come up with a way to do that. We would need to do a little bit of background research, and we can do research to learn a little bit more about the way that electricity flows. I think we could absolutely find out if water is a good conductor or not.
Okay, and we could definitely build an experiment or design an experiment to help us.
I think that we can design an experiment to help us. But before we get there, we have to make sure that we have a hypothesis.
Okay, so back to our steps.
Yes.
Okay. So step one was make observations and ask a question. So we're going to use all of our senses. What do we see? What did we feel? What did we taste? We're not tasting anything today. If we smelled anything, and what am I missing?
See here.
Here.
Oh,
Did we say
yes.
here? It was here,
It was
right?
here.
Okay. And so we're looking at everything our senses around us. And then we're looking at what we have, our experiences, and maybe the observations that we've had when we've been in class, right?
Yeah.
And just life, our observations. And we're going to ask a question. And our question for this experiment is, does water conduct electricity?
Okay, we can figure that out for sure. So we would do a little bit of research to see if we can learn more about water conducting electricity. And we could do that through the types of things that we've been doing here today. But we can also do some additional research by talking to our teachers or reading books or going online and watching videos. We can do other experiments and include the information we learn from those experiments to help inform this experiment.
Okay, and so I'm going to take all of my observations from step one and my research from step two, and that places us at step three, because you did not want me to forget to make a hypothesis before doing an experiment. Okay, so when we form a hypothesis, we're using all that we know to predict what we think will happen.
That's right. Let's see. What do we know about water and electricity? I mean, I was nervous to put water with the Van de Graaff because I've always been taught that if you have wet hands, you shouldn't plug something in or use a light switch.
And I've been told that too. I've also been told, and maybe students, you've been told, that you have to get out of the swimming pool when the storm, lightning and thundering, is in a certain area or proximity of where you are swimming.
So that makes me think that there must be something to this. Water and electricity thing.
Yeah, it sounds like water is that key component to not touch the electric switch and not be in the swimming pool when now we know that lightning is electricity. So I'm thinking that our hypothesis is that water is a conductor for electricity.
I think that's an excellent hypothesis. And I think that we can develop an experiment to test that hypothesis. We'll need to find some materials to be able to test that. What do you think we need?
Well, I know that we're going to need water.
Yeah, I definitely think we're going to need water. We have some here. I think that we're also going to need some stuff to be able to make a simple circuit. So I think we're going to need a battery and some wires with alligator clips. We're going to need maybe some aluminum foil And I think we're going to need a light. Good thing you've got all of that here. So we can construct a simple circuit here to help us to test this idea that water is a conductor. We've got distilled water here. I think we can use that, but we're going to need a cup or something to add the water into our circuit.
Okay, and so I have the cup and it's labeled distilled water. And I know that distilled water is a pure form of water. It has gone through the distillation process. And in that process, water is boiled. And once it's boiled, it releases steam. And when that steam is cooled, then it returns back to water. And that is the distilled water. Is all of the water I use every day distilled?
No. Most of the water that you come in contact with whenever we talk about washing our hands or being in a swimming pool is tap water. And tap water is not the same as distilled water.
Okay, well, I didn't bring any tap water today.
No, and we don't have a sink here in our studio. So I think we're going to have to see if it's possible for us to do something else.
Okay, so are there certain characteristics of tap water that we can like make something that might resemble tap water?
Yeah. Tap water has things dissolved in it. Tap water contains salt and other solutes dissolved in it. So I think that we could mimic tap water by adding some salt to our distilled water, and it should act pretty much like tap water.
Okay, so I'm on board with that we would have distilled water and then we would have what would resemble tap water. But why do we need two types of water?
That's a great question. What we're about to do is something called a controlled experiment. And in a controlled experiment, it's important that you keep everything constant and the same, except for the one thing that you're testing, which is your variable. So in this case, we're going to have distilled water in our circuit, and we're going to see if our circuit lights up if we conducted electricity. But then we're going to try it with our tap water simulation, which is in this case salt water, to see if our tap water would conduct electricity as well.
Okay, so in the controlled experiment, we have one varied element or one varied component. And in this experiment, it's the type of water.
That's right.
And everything else stays the same. So we'll switch out our cup of water and keep our circuit the same. That way, if we get different results, then we'll know it's due to the type of water.
That's right.
Okay. Well, let me grab a cup for our salt water.
Okay. And I think that we also need to remember that we need to wear our protective equipment. Anytime you do an experiment, it's important to keep yourself safe. In this case, we're working with water, so we are going to put on some safety goggles so that we don't get any of this splashed into our eyes. So we've got our safety goggles on and ready to try this experiment. Okay, in order to make sure that the results that we get are due to our change in water, let's first test our circuit. Right now, our circuit is open. So we have a battery here that can provide power, and we have a light bulb here, but the light is not on. The light's not on because our circuit is open. If I close the circuit by touching these two things together, what should happen to our light?
It should illuminate.
I think it should illuminate. Let's test it and see if our circuit works.
Yes. Right. Can you see the light is shining?
Our circuit works. It looks pretty good reflecting on that table.
Okay, great.
Okay, so if we now take our cup of distilled water, which we hypothesize should conduct electricity.
Yep.
We think that we will have electricity that passes through the water. And what should happen to our light?
It should illuminate.
It should illuminate. Let's see. Let's see what'll happen. Let's see. I'm going to move this over here so you can see our light. Can you see our light?
Is it on? I can't see.
Is it on?
Is it on yet? It's not on.
Why isn't it on? I thought that the water would surely conduct the electricity, but it's not conducting. Well, let's see what happens with our tap water. Remember, we didn't have any tap water here in our studio. So we have some distilled water, and we're going to make it sort of like tap water by adding some salt to it. We're adding salt, which will dissolve in the water and separate into ions and be very similar to what we have in our tap water. So we've made some tap water here. And let's see what happens whenever we use our tap water instead of our distilled water.
Well, now I'm not too hopeful because the distilled water didn't turn on. So this is probably not going to turn on either.
Well, gosh, I wonder why they make those rules then. Let's see.
Wait, the light turned on. What? And it's not touching in there,
No.
but the light is still on.
What in the world?
Okay. Well, wait, put it back in the distilled water.
Let's put it back in the
Maybe
distilled
it
water.
actually works in distilled. No, the light's not on. Okay. Well, back in the salt water.
It works. What's the difference here? What is going on?
Okay. So I am so glad that we developed a controlled experiment because now we know for sure it's because of the type of water. But why did it turn on in the salt water or what resembles our tap water, but not distilled water?
Yeah, this is really strange. I'm not sure why we would have something with salt in it that conducts when the water didn't conduct.
But we developed our experiment and we did it, right? We conducted it and then we looked at our results. So that brings us to step 5.
That's step 5.
Okay, so in step 5, we are analyzing our data and drawing conclusions.
That's right.
Okay, so it has to be what's in the salt water.
It has to be. And in this case, what's in the salt water are ions, which have a charge. And so just like we have in the metals, when we talked about how the metals would allow electrons to flow freely, the ions in the salt water will also allow the electric current to flow freely.
And so our salt water was not pure. We know that distilled water is a pure form. So our tap water has impurities also?
Exactly. Our tap water is more like the salt water. It's got ions in it. It's got lots of stuff that could conduct electricity. So because it's got all of these impurities dissolved in it, our tap water will conduct electricity. So that's why we have all those rules.
So that's why if I go to wash my hands and I hurry out, I don't dry them completely, I should not touch the light switch. And that's why if I pick the wrong day to go to the swimming pool, that I have to get out when the storm approaches.
Absolutely. I think that's really great that we were able to relate what we learned here in this controlled experiment to our everyday lives.
It makes a lot more sense now that I understand what's actually happening and they're not just rules for me to follow.
Exactly. And so it's really important that we finish our experiment with the 6th step of the scientific method, which is to communicate your results. It's most important that after you do an experiment like this, you let others know about it. This is why there are scientific journals out there to communicate results. If you were to do an experiment, you could write a report, you could create a poster, do a presentation, or just have a conversation with somebody and let them know what you've done so that they can share in your knowledge and learn from your experiments.
I've learned so much about the Graaff. I've learned about making observations and how observations can help develop experiments. It helps me to even ask a good question. We've thought about the scientific method that's helped us to develop an experiment. We've tested it. We've determined that our hypothesis was kind of true, right? We were kind of correct.
Yeah.
But it wasn't water. It had to be water with impurities in it because our distilled water was not a good conductor.
And it's okay that we were not right in our hypothesis. We learned something in the end. And so I'm really glad that we still did this experiment and got to find out something new.
Yeah. Well, I guess we're coming to an end now, right?
Yeah, we are coming to a little bit of an end here, but I think that it's really important that we all remember that it's good to know this type of stuff about electricity and basics about atoms because everything builds off of the basics. So if we understand how the world around us works, That's going to help to turn you all into the types of researchers who are doing research like the folks at DTRA, who are protecting us by learning the answers to lots of different types of questions. So we explore a simple question like this now, so that later you will be able to tackle the complex questions that will come to you as an adult.
Yeah, and as they make observations in class now and in their next classes and with their teachers and with their friends, that as they have more and more observations, they'll be the ones asking the questions that have never been asked before.
And that's exactly what we want from you. So we are so glad that you all joined us today for the Discovery Fest. And we want to send you out with one last demonstration. I hope that's okay. I think we have enough time for it. So what we have here is a Pi 10.
Back to our Pi 10.
We remember what happened to our Pi 10 when we put it on our Van de Graaff. What did it do?
It flew away. Flying saucers. I don't want any more flying saucers, though.
No, I don't want a flying saucer either. So I think we can hold it down like we did with the octopus with a magnet.
Okay.
So let's put it on the Van de Graaff generator, and we'll put this magnet here.
And so the magnet should hold the Pi 10. And if there's anything in the Pi 10, what do we think will happen with it, to it? If it's light enough, right?
Yeah,
If it's light enough.
our great questions, it's got to be light enough. So if we have something light in the Pi 10 and we turn the Van de Graaff generator on, our dome will become positively charged, and it will need to steal electrons from the things that it comes in contact with, like the Pi 10, which will become positively charged. And it would steal electrons from the things inside of it, which would become positively charged and repel from one another, right?
Yep.
Well, let's give it a try.
Let's see.
I'm going to put this grounding rod on our Van de Graaff for right now while it gets started. So right now, the grounding rod is keeping our Pi 10 from becoming positively charged and the contents. But if I take the grounding rod away, it's a party, it's a science party. I've learned so much of what a great light. And look, it's on me, it's on you.
Students, this has been so much fun, and this is great. Thank you so much for your time today. We hope that you've learned something new, that you will remember the scientific method, that you will continue to make observations and enjoy the world of science. Thank you so much for your time, and we hope that you continue to enjoy the Discovery Festival.
Bye.
Bye.
Thank you so much to the Defense Reduction, oh my gosh, I'm losing my mind. Defense Threat Reduction Agency for that super fun demonstration. Our staff here at our physical location loved the Pi 10s and the streamer octopus arms. So exciting and cool. DTRA is a longtime supporter of Big Brothers Big Sisters and an amazing organization. So we really enjoyed being able to host you. Teachers and students, thank you for stopping by. We have 3 other demonstrations today. At 11, the Nuclear Museum of Science and History will be talking about nuclear energy, how nuclear energy is used in space exploration. The education plan will be on at 1 p.m. to talk to students about the importance of saving up for higher education with a fun Jeopardy game. And Math Hoops will be holding a special presentation for educators to do a demo of their board game. So thank you so much again to the Defense Threat Reduction Agency. You guys are amazing. We love you so much. Have a great day, everyone.